box, I can export it for my record, Tensile record.
Updates on Moodle. Introduction section, I didn't make any updates so far, but on Tensile test experiment, there are two files that I updated, and there's one link. So I will explain these files one by one as we go through our lessons today. But the one thing I want to mention, due to this hurricane, university was closed, and it's closed till Friday. So regular operation is not, regular process is not working on campus. So I wasn't able to go to my lab and finish the experiment. What I am planning to do today, I will give the lecture and prepare you guys to write the report, the theory section, and the data and results section on a spreadsheet. So I will go over this spreadsheet, how to prepare the spreadsheet using the given data, measured data, and how to put it on a lab report. So this is going to be the important section for today's lecture. What we're going to do with the experiments, once you guys learn how to develop a spreadsheet and how to put a report together, you're going to be waiting for the data. Once I run the experiment, I will provide the data for both specimens, steel and aluminum. I will add a couple more files and a couple more links on this section, Tensile test experiment, so you can check it out later today. Okay, let's continue. So the objective of the tensile test experiment is basically to determine, in theory, we're trying to determine and draw the stress and strain curves for the steel and aluminum specimen. But why do we need the results from this experiment? What will be the reason that we need the results from this experiment, in simple terms? Anybody has any idea why do we have to test different materials and compare the results?
Isn't it important to know the amount of stress you can put on a material when you're using it for like a product that you're going to make?
Right. If you are on the design stage, if you are designing, let's say, a beam or girder or column, you want to know, first you want to know how much load you can apply to this member before failure. So you want to know what is the maximum stress that you can apply to this specimen or to this girder or column. In order to know how much stress this specimen can take or the element can take, you should test it before you use it. In the industry engineering field, if I'm the design engineer, I go back and reference to my steel manual, and I can pull up what is the ultimate tensile strength or the tensile yield strength of this material if it is a steel. If it's aluminum, I can refer back to aluminum supplier, and I can get the characteristic of the material that I'm going to be using in my design. Now, go ahead. Can you mute please? Okay. So tensile, in other words, tensile testing is one of the simplest and most widely used mechanical tests. By measuring the force required to elongate a specimen to breaking point, material properties can be determined that will allow designers and quality managers to predict how materials and products will behave in application. So when you put your design in service after the construction is completed, you want to know, you want to basically forecast how it will behave in advance. So once you test your material, you know the critical load that that this material can take, maximum load. So you want to be in the limits. You want to be in the safe zone, so that you can finish your design and you can have a safe design and safe construction. Let's put it this way. Also, again, as an engineer who is designing this something like designing this member to carry loads, he or she needs to know the minimum strength of the material he's using so he can calculate the correct safe loading. Let's say if you're designing an elevator, in this case, you need to state how many people who can be in this elevator. If you know how many people and if you have the X amount of load that's going to be applied to this elevator, you can design your elevator in efficient manner. So it can be cost effective. So you're looking for the cost effective design as well. You want to look at the strength ratio, strength and the dollar ratio. In this experiment, we are comparing. In this experiment, we are comparing aluminum and steel. One material is lighter than the other. One material is expensive than the other. So we want to know which one is more suitable for our design. If we are designing something for a project, you want to know which material is more suitable for your design and which one is more cost effective. And this is the whole purpose. But when you look at this technical explanation of objective,
Turn your shit off.
can you please mute?
What did you say? She said, turn that shit off.
Ahmed, can you please?
Hey, Helen.
Everybody, can you please mute unless you want to say something? Thank you. So the objective, when you look at this theoretical objective, you might be confused because I believe that some of you don't know what is the term of stress, what is the terminology of the stress, what is the definition of strain. But in simple terms, I explained it is just to know what is the ultimate or minimum strength of your material that you are design.
How am I going to take notes? I don't know. I don't need to take notes.
Claudia or Chloe, can you please mute? Everybody.
Ahmed, mute.
I can still hear you. Okay, now it's good. Now it's good. So in this experiment, we're going to use several equipments, one of which is Tinus Olsen UHTM. And you can see this equipment on the right side, upper right corner. UHTM stands for Universal Hydraulic Testing Machine. And with this machine, actually, we will be using this machine for this experiment, also for concrete experiment, concrete compression test. We can use this machine to apply a tensile force as well as compression. In the upper section of this equipment, it's used for the tensile testing, but the lower portion is for concrete compression testing. And the second equipment that we'll be using will be this extensometer. An extensometer is a device that is used to measure the changes in length of an object. It is useful for stress, strain measurements, and tensile tests. Basically, you're going to be attaching this piece of equipment into your testing specimen to measure the elongation and the change in length as you apply loads on your testing specimen. And then we will use gauge punch. Gauge punch is going to help us to punch two holes on a specimen. If you go back to previous slides, in this specimen, L0 stands for gauge length. And in order to measure this gauge length, we have to punch two holes and measure whatever is the gauge length is. And in our case, in typical tensile test specimen is 2-inch gauge length, basically. So gauge punch is used to punch these two holes. And then you use hammer to punch the holes, and you use ruler to measure the length. And micrometer is used to measure the diameter of your specimen. So you have to measure the diameter as well. Don't be scared if you don't understand the terminology in this part. If you don't know the equipments, I have a simulation. We will be looking at the simulation and we're going to run this experiment and simulation. and we will look at the YouTube video before we run our own experiment, hopefully next week, before we get our own results. And then our two specimen is, first one is steel round bar, this one, and the second one is aluminum. Okay, so let's start with the simulation. So I will drop this link as on Moodle, like the other ones. And you should run this experiment, the simulation experiment, by yourself after this class, before you get the result from our own experiment next week. It will help you to understand the theory and the procedure and the results. If you don't run this simulation before you start your experiment, before you start your lab report, you will have so many question marks. So it will help you to develop your report, and it will help you to analyze the data. So first thing is we need to state the problem. What is the problem? To properly design a structural or mechanical component, the engineer must understand and work within the characteristics and limitations of the material used in the component. I mentioned this in simple terms at the beginning of the class. Also, materials such as steel, aluminum, plastic, wood, each respond uniquely to applied loads and stresses. To determine the strength and characteristic of materials such as these require laboratory testing. One of the simplest and most effective laboratory tests for obtaining engineering design information about a material is called tension test. So you can use this section, you can summarize this section to write your report. So we know what the problem is and we know why we need the result from tensile testing. Is there any questions so far regarding the objective, regarding why we are here, why we're running this test, why we are looking at this tensile test?
So just to confirm, are we going to do this experiment next week?
Yes.
Okay, so we don't have to write a report for next week. It's going to be the week after that, right?
No, we don't have to write a report next week.
Okay.
But you should take notes, and you obviously you're going to have the PowerPoint, and you will have this link, how to run the experiment in simulation mode. And when we run our own experiment next week, it can be, probably it's going to be on Monday. I will check that with the department, and then I'll post the video on YouTube for you to see, and we can discuss the video when we come back next week on Wednesday.
Okay.
So you will have your data by Wednesday, and you can start your report when you have the data. But if you want to start in advance and to develop your objective and theory section or equipment section, is shown here. I have a sample report, steel and aluminum tension test. You have your title page. This is the way you need to construct your report. You should write your name, your signature, and the timestamp. The title of the report again, and the objective. You can keep the objective short, as it was stated on the PowerPoint. You go back to PowerPoint, you'll see the objective. And the equipment used, and the experiment. This is the experiment, the background, and the theory section. So whatever is on the PowerPoint and the PDF that's on your Moodle, you can summarize it, and you can construct your theory section. But you will be waiting for the results because we haven't run our experiment yet. So once we get the data, I will show you guys today. Actually, I will show you how to use a spreadsheet, and I have an example. And you have this spreadsheet on the Moodle as well. So you will get an understanding how to develop this table. But step by step, let's continue our simulation. Is there any other question?
Are you gonna post that on Moodle?
Which one?
The file that you just showed us.
Tension test? Yes, I will.
Okay.
I will. Okay. So we already know the problem statements. And then we're gonna go to tension test setup. So in this picture, you see the upper grip and lower grip. And this upper and lower grip is here. So if you look at the upper section, and this is lower section, and you have a tensile test specimen in the middle. Also, they are measuring the gauge length with a equipment. I forgot the name. Sorry. So anyway, to conduct the tension test, the specimen is inserted into grips, upper and lower grip, which hold the specimen securely while tension force is applied by the testing machine. Generally, lower grip remains stationary while the upper grip moves upward, thus creating tension in the specimen. So the bottom portion, lower grip, is fixed and the upper portion is moving upward. So if one part is fixed, one end is fixed, and the upper portion is moving, you obviously applying a tensile force, and indirectly you're applying a tensile stress into the material. So in this section, it's explaining what type of grips are used. In our experiment, we will be using wedge type V-shaped holder. It is used for plain, round, or flat specimen. So we have round specimen, circular cross section. We will be using wedge type grips. In this section, it's explaining what type of testing specimen is used. In our case, we will be using the threaded specimen. It's called offset thread, but let's read this section. Some tension specimens are machined by cutting threads on the rod ends and reducing the diameter between the threaded ends. Threads of this sort are called offset threads. This is exactly what we're going to be using in our testing. Since the rod diameter at the end is larger than the specimen diameter, the presence of the threads does not reduce the strength of the specimen. Tension specimens with offset threads are attached to the testing machine with threaded specimen holders, which eliminate any possibility that the specimen will slip or pull out of the grips during the test. So if there is any slippage during the experiment, you will get a wrong result. You're not going to get an accurate reading. So if there is any slip, you might get high elongation, which will give you a goofy graph. So you're not going to be able to analyze the data because you put the garbage in and the computer will give you garbage out. Let's go to the next page.
17-year-old with the AR.
One of our equipments that I already explained, it's called extensometer. It is used to measure the elongation in the tension test specimen. The extensometer has two knife edges, which are clipped to the test specimen. It's not shown in this picture. This equipment was the extensometer, by the way. I forgot to name, but now we know it. The initial distance between the knife edges is called gauge length. So you should record the gauge length, and I will measure it during the experiment. But our tested specimen has 2-inch gauge length. As tension is applied, the extensometer measures the elongation that occurs in the specimen over the gauge length. So as you apply load, the extensometer is going to measure the elongation, and we're going to be recording the elongation corresponding with the applied load. In this section, it's explaining how precise measurements you can have with the extensometers. Okay, so several measurements are made before during and after the test. And we will record it on the, I will record it on the spreadsheet, and I will provide this spreadsheet to you guys. It's on Moodle, and I will pull up the spreadsheet so you know what we are measuring before and during and after the test. Let me pull up this spreadsheet. So this is the spreadsheet sample test data, tensile test data spreadsheet template. So you can use this template in order to develop your own tables and graphs. So I prepared everything for you to input the data, measure data, and calculate the stress, strain, and Young's modulus, whatever is required. And I will mention that what you need to get using the given data. So before the experiment starts, you need to measure the diameter. So we're going to use the micrometer to measure the diameter of the specimen for each specimen, aluminum and steel. Once you get this, you can calculate the cross-sectional area, and the equation is already in this cell. And if you want to look at the notes, you can look at this note section. Over here, the area for circular cross-section is given. And then gauge length. It is denoted with L naught. I mentioned before in the equipment section how we measure the gauge length using the gauge punch. We use the gauge punch and punch 2 holes on the specimen and measure the length. And it is 2 inches. And I will measure it again. It will be 2 inches. Every semester, we do the same thing. This is what you measure before the experiment starts. And then we're going to come back here again to measure the final diameter, etc. Let's continue our simulation. Okay.
So are we allowed to use that chart for the
What chart?
experiment?
What chart?
The Excel sheet that you just showed us.
This
We
one?
can actually use this? Yes, sir.
Yes, of course. So,
Okay.
so if you go to your Moodle, first I want to get confirmation from one of you. If you can tell me that you have this tensile test data spreadsheet template and sample tensile test calculation and results. If one of you guys confirm, can you guys confirm?
Yeah, we have that.
Yes, we do.
Excellent. Today might be a little bit longer because I want to cover the background, like the theory section in details, so I don't have to respond tons of emails. So I want to get into details, explain how the spreadsheet works. And I usually don't share the spreadsheet with the students and the sample calculation. But since this is unique situation, coronavirus, COVID-19, we don't have face-to-face class, I try to make easier. And it's actually easier to teach online when you are working on a spreadsheet. Anyway, let's continue the simulation, and we're going to go back to tensile test data spreadsheet, and I will explain the remaining portion. So before the test, the cross-sectional area of the specimen must be determined. And I mentioned how we did it. I demonstrated how we measured the diameter using micrometers and then use that data to calculate the area. The area will be used. The area will be used with the force data to compute the normal stress. So there's one equation that we're going to use, and you need to be familiar with the equation if you have not taken mechanics of materials yet, or if you are a sophomore. I usually ask this question, how many of you guys take in mechanics of materials right now? But if I ask this question, it will take 10-15 minutes to get answer from the students. I can see the students. So this equation, let me go back to my spreadsheet and explain what this equation and how we use it. So we get the cross-sectional area, and we are trying to calculate the normal stress. Okay, we come back to our spreadsheet. There is a stress equation right here. It's P divided by A. P is the applied load. So we're going to start applying loads, starting with 1,000 pounds. It's going to go to 2,000, 3,000, 4,000. As we increase the loads, we're going to measure the elongation automatically with the extensonometers. So let's say it's 0.001, 0.002, 0.003, etc. But if you look at this column, I don't know the information. What is stress? How much stress I'm applying to the specimen in order to get this amount of elongation. There is an equation, stress equation, that is P, applied load, divided by the cross-sectional area. And I have my cross-sectional area calculated in this cell. I write my equation, I lock the cell, click enter. Something is wrong because there is a minus sign in front of it. So now I know how much load is being applied, but this number is not quite right because it's 5,051.8 KSI. KSI is too big, it's too much stress. So I'm assuming there is some calculation error or unit error. So I look at the applied load, it is in pounds. But I look at the stress, it's KSI. And I can go back to notes and I can look at the conversion units. 1 KSI is equal to 1,000 PSI. How I know this? Because I know 1,000 pounds. I'm sorry, 1,000 pounds is equal to 1 kip. So I can come here and I can divide this 1,000 pounds by 1,000 to convert it to kip. Come on. Right here. Jeez. Or let's put it in KSI.
I think you have to multiply it.
Something is wrong. Yeah, I'll fix it. That's okay.
I think it's a.
Let's put it let's put 1 KSI and 2 KSI, and I can change the unit. So either way, you know the unit conversion is here. You can use this conversion table, or you can Google it anytime. You can convert from KSI to PSI or pound to kip. So you should know that 1,000 pound is 1 kip. So now I put it on 1 kip, and let's calculate it again. It is 5 KSI. And if I break down the cells, I get the stress corresponding with the elongation. But I also need to have the strain. So we're going to get the strain rate calculations when we get to the strain stage on the simulation. Let's look at the next section. Okay, the gauge length of the extensometer should be known. So we already noted that the gauge length was 2 inches. The normal strain will be computed from the specimen deformation. In example, the axial elongation and the gauge length. So how we do this? To get the strain, you have the equation, elongation divided by gauge length. So I know this elongation data given by the software or extensonometers. I use this data and divide it by the gauge length, but I need to lock this out. I get my strain. So the gauge, is important to calculate the strain. Hello?
Yeah, I just received my call, so I have to go.
Okay.
All right.
During the test, the force applied to the specimen is recorded, and you have seen on the spreadsheet. During the test, this part, the force applied by the load applied by the machine to the specimen is being recorded up to the failure. You're going to start from 0 to the failure. And then the elongation in the specimen between the extensorimeter and knife edges is measured. So this elongation between the extensorimeter and knife edges is recorded. So we're going to start with 2-inch gauge length, 2-inch gauge length. And in previous years, obviously this data was measured in, I think, last semester. The specimen elongated 0.72 inches. So we got this length as well. And after the specimen has broken, the area of the cross section at the fracture location is measured. Reduction in area between the area of fracture surface and the horizontal cross sectional area. This is the reduction in the area. Is divided by the original cross sectional area, which provides one measure of the ductility of the material. So if you get the ratio of the cross section before and after, you can measure the ductility of the material. The term ductility describes the amount of strain the material can withstand before fracturing. You can either use the cross sectional area before after, or you can use the length before after to measure the ductility. So if you come to the spreadsheet again, you will see ductility. And in this case, I'm calculating the ductility using the final length minus gauge length divided by gauge length times 100, and it will give me the percentage, 36% ductility. I should perform this calculation for both specimens, steel and aluminum, and compare which one is more ductile, which one is more brittle. Okay, next. So in this stage, we are conducting the test, and the tension test will now be conducted for an aluminum alloy specimen. In this case, the simulation only allows for us to look at the data from the aluminum alloy specimen. So click and start it. Okay, if you look at the simulation, it's already started. We are increasing the loads and elongation is increasing. We're gonna run this stage couple times to understand in detail. Let's run one more time. If you notice at the beginning, the plot is linear, and that linear portion is the elastic region. And when you hit the certain point, which is called the yielding point, the plot start curving. One more time. I wish I can stop this. So in this stage, deformation is increasing much faster. That's correct. So you increase the load and you see the deformation. I mean, you don't increase the loads too much as opposed to the formation that you observe from the specimen. But in the first stage, your material is acting elastically and it's not deforming. Imagine you're applying 10,000 pounds up to 12,000 pounds in the linear portion of the graph, and you only see up to 0.04, 0.03 inch deformation. But on the other, once you reach to 12,000, you increase only 2,000 pound loads extra to the applied to the specimen, and you see the deformation. You can read it. It goes to 0.1 from 0.03. But if you look at the ratio, you can tell that this specimen already yielded, and it's deforming without sustaining more load. But eventually, it is going to the ultimate load capacity. So when you look at this higher portion, the upper portion, around 15,000 pounds, this is the maximum load that the material can withstand before failure. And eventually, material fails around 13,000 pounds. So this will be the graph that you will see when you plot load versus deformation. So you can go back to your spreadsheet. If you are looking at the spreadsheet on your computer, I have I have only 2 graphs, and those are specifically for still specimen. One is for stress versus strain graph. One is in detail, stress versus strain graph. Now I'll explain why we need the detailed graph. You can also add the load versus deformation graph by using only these 2 columns. But in these graphs, if I look at the data section, I only have my x values, my x-axis. My x-axis is having the strain values here. And my y-axis is going to be representing the stress being applied. So these are the dummy numbers. So you're not going to end up with this graph. And I will show you on the sample calculations what will be the perfect graph for the tensile stress strain diagram. Let's look at the sample calculations. This is from 2017. I found it earlier today. So after having the raw data, stress and strain is calculated, as well as Young modulus, you can compute these numbers by entering the applied load and elongation to the spreadsheet, and you can aim to get these results. Obviously, if you are not getting these results by inputting these raw data, something is wrong with your calculation. So you can go back to spreadsheet and correct your work.
Excuse me. I was wondering, you see how it goes from like 1,000, 2,000, 3,000 now? It's like a consecutive 1,000, and then around 9,000 it, isn't 1,000. Is there any reason for that? Like,
no, we are taking measurement at 1,000, 2,000, 3,000 I mean, I can take measurement at 500. It's up to me. So I take measurement at 1,000 and 2,000. There's no reason. It's just to keep the consistency. That's it.
Cool.
No problem. And there's one, like if you pay attention to this section, thank you for paying attention to the details. Sorry. If you look at the sections after 8,000, I'm taking measurements at 0.01 increments in change in length. So I look at the elongation, and I take measurements by looking at the extensonometers, and I'm recording the applied loads. First, I take measurement on elongation by looking at the applied load. And when I reach a certain point, I change it. I look at the elongation, and I record the applied load. But it's up to you. It's up to the instructor. It's up to the testing technician. If you are following the instructions, it doesn't matter which increment you're using, 1,000, 2,000, or 100, 200, it will give you the accurate information as long as you get the correct reading. Every time when you look at the applied loads, and you should look at the elongation on the extensometer at the same time. So you want the instant elongation corresponding to applied load. There is no reason behind it, actually. So based on these results, I can now develop my table, my graphs. So all I want to see in the graphs, I want to see the labels. What is this graph? I know by looking at this graph, it is stress, strain graph, stress versus strain graph for steel specimen. And if I look at the x-axis or y-axis, on the x-axis, I have my strain measurements, and on the y-axis, I have my stress. So when you are writing your report, when you are working on these graphs, and then next section is the important turning points. Let's put it this way on the graph. So I want to know what is the ultimate tensile strength of this material. And also I want to know what is the fracture strength. So if I'm, as I said at the beginning, if I'm designing this beam, girder, or elevator, whatever you're working on, I want to know when it will fail and when it will start to fail, right? If I look at the ultimate tensile strength, if I apply 73.77 KSI stress on this material, if it's a beam, girder, or column, I know it can withstand up to 73.77 KSI. But eventually, if you sustain this load, it's giving up and it will fracture at the lower loads, lower stress. But this section, linear section, which is called the elastic portion of the curve, this is the safest region that we try to stay in. So the designs, the steel designs, speaking of the structural engineering perspective, this is the safest zone. This is the zone that we are working on. So if we are selecting a material, we use the yield strength instead of ultimate tensile strength. Because if you use the yield strength, you stay in the safe zone. So your design is safe even if you have 50 KSI loads and or 49.1 in this case. So it is hard for me to read this graph in the general format because I need to zoom in and I don't know what the value is between 40 to 60. So I can have another graph, I can generate another graph and I can look at it in detail. So I only add certain portion of the data up to here, certain data points. And I can use 0.2% method. I can draw a line parallel to the linear portion, and I can read the corresponding stress, which will give us the yielding point. So below this point, up until this point, 49.1 KSI, this material is behaving elastically. In other words, if you remove the applied loads in this material during the testing, if you stop loading, if you start unloading, it will go back to original position. So imagine if you have a rubber or if you have a razor in your hand right now, you can start pulling. And when you leave it, when you unload the rubber or eraser, it will go back to normal. Still acts the same way up to a certain point. If you go beyond this 49.1 KSI up to ultimate tensile strength, your specimen or your member will undergo permanent deformation. But in the first region, the elastic region, the formation is not permanent. It is temporary. As soon as you unload it, it will go back to original position. Any questions so far? No. Okay, let's
Do
continue.
we,
Go ahead.
I'm sorry, the, the, the graphs that you just showed us, do we have to do those as well? So there would be 4 different, graphs?
Yes, including aluminum specimen, you should have 4 different graphs.
Okay, thank you.
Okay, no problem. Any more question? No. Okay, let's continue. So we know that bang, the specimen breaks. So we fail the specimen at 13,620 pounds. Let's see what's next. I just found this one. So I just found this simulation earlier this morning because I was thinking of what I was gonna do in this lecture and how I was gonna demonstrate without having the proper equipment and proper testing machine. But I believe that this simulation is well enough for simulation purposes for the tensile experiment before we run our own real-life experiment. Oh, I was just explaining the unload and reload behavior. So this is the perfect section. Let's look at the tension test again, but this time we will explore another interesting characteristic of material. Halfway through the test, we will unload the specimen and observe the response. Let's see. Sorry for the delay, but it's coming. Okay. So once again, you notice that the linear portion, it is still linear. And past a certain point, the plot starts to curve right here. And let's pause here. The simulation pauses here. And we know that the load at this point is 13,230 pounds. So at this stage, we stop the experiment. And in real lab experiments, every semester, we stop the experiment. And then we go back before this curve. And when we start unloading, material goes back to original position, to 0. But let's see what's going to happen in this case, because we passed the yielding point. Let's see if it's going to go back to original point or it will have the permanent deformation. So as you can see, the specimen is having the permanent deformation. So all load has been removed from the specimen, but its deformation is not 0. The specimen has been permanently deformed, like I said. Let's do it one more time. Specimen uploads along a line parallel to the initial linear portion. But if we were unloading this specimen right here around 10,000 pounds, you're going back to 8,000, 6,000, 4,000, 2,000, eventually zero load, you will go back to 0 deformation because it's elastic region. But beyond that region is the plastic. And I believe in the spreadsheet, I mentioned the elastic and plastic region. So don't be confused with the elastic and plastic region here. You can always extend. I can change the borderline of the elastic region if my numbers are not matching with the elastic region. So in previous years, previous semester with the results, my elastic region was only this section. And my plastic was starting from here. This is the reason I'm using these two borders, this border between elastic and plastic region. So if your numbers are different, you can merge, unmerge it. And if your elastic region is up to this point, you can merge it again, and you can change your plastic region right here. You can adjust it. So you can always adjust this and show it on the report that you know what is the difference between elastic region and plastic region. So any question between elastic and plastic region? Or who can tell me the basic difference between elastic region and plastic region? What is the main distinctive subject between elastic and plastic region?
Supposed to just kind of shout this out loud, but isn't elastic like right before it hits the deformation point, and then plastic is right after?
So the specimen starts deforming right at
The
beginning.
elastic region, it'll go back to its original form.
Right.
In the plastic region, it's permanently deformed.
Right. If you know this, you're okay. Because you know you don't want to deform your member in your design permanently. You can allow to deform your member elastically because you know that when the load is removed, you're okay. Let's look at in the case of bridge. If you're driving from West Bank to the city, that bridge is shaking all the time. Sometimes we have 18-wheelers, sometimes we have small trucks or large trucks, etc. But bridge is deforming every time it sustains a high amount of load. In the case of, let's say, two-story structure, the floor plan, you look at the floor plan, you have your beams, girders, and you have your columns. Let's say this floor plan, in this structure, the second floor is used for library. In the library, you have the stationary loads, which is the dead loads. The library, all those books and the other equipments, the load is sustained on the loads bared by the beams and by the, or if it's concrete, it's by rebar and concrete. But every time when people start walking into the library or classroom, you are increasing the loads. But when the engineers are designing the structure, they know and they specify the maximum occupancy. But if you go to any classroom or if you go to a movie theater or library, you can see the maximum occupancy. Because they know this section of the structure or the building cannot sustain more than, let's say, 100 people at a time. If it does, then it's going to have permanent deformation. Then it's going to require rehabilitation, and it's going to be costly. So in order to avoid these issues, you work on the elastic region and you specify the maximum load that your material or your member can bear in the service condition. I don't know if it's clear, but as long as you are in the elastic region, you are safe. So you specify your material strength on your design, so that during service condition, your members or your frame, your construction, your structure is not overloaded and doesn't fail. Okay. Let's see what else we have.
I have a question.
Yes, sir.
Is the elastic region the range that is linear?
Yes.
And the plastic region is whenever it starts to curve? Is that how was the?
Mm-hmm. Okay, elastic region is the linear portion, and when there is a change, when the change starts from linear region, from linear region to curve, that's where your yielding point is. And in this point, you are leaving the elastic region and you are getting into elastic region.
Okay, I got it. Thank you.
Okay. Let me see if I have the PDF that I was gonna give you guys. But I think I can pull it up. So give me 1 second. I'll pull it up in a second. Okay. So in this stage, in the previous stage, we already unload the specimen, and now it's being loaded again. We reload it. And as you can see, when you start loading it, it is starting deforming from the point where it left off at 0.0, between, I think it's between 0.05 and 0.1, right here. And then it continues, moves forward as it was supposed to. And at the end, specimen breaks again at the same location.
Well, I have a question.
In your report, you're not required to talk about the unload and reloading behavior. We're only responsible for the plastic and elastic region. But you should know the difference when you unload and when you reload, how the material will behave when you unload the material during the testing and reload it. But you're not required to write it on your report or do the calculation. Yes, go ahead.
So if you load the material and then unload it and then load it again, do you start over with a new elastic period that starts at the new elongation?
No.
Yeah, what exactly did he do?
What exactly, what?
Like, what exactly did he do? Like, what did he physically do? So he broke the beam, and then what did he do?
So beam has not failed yet. Or no, it's not beam, it's this testing specimen, circular shaft. It hasn't failed yet. You just stop the experiment when you're running in the middle, right here. You stop applying load around 13,000 pounds, and then you start unloading. You go back to 12,000, 10,000, 8,000. When you start decreasing the load, the formation is decreased as well. But when you start loading again, reloading, you start from 0 and you go back to 13,000 again, and then it starts deforming because it already deformed in this section. See, it's starting from 13,000, and you can
So
see.
if it's already begun to deform, there's no going back. Like you can't reduce the load and then get some elasticity out of it after.
Right, you're right. For example, if any of you has ever done any inspection at a bridge, on a bridge or on a structure, pretty much every year, it depends on the maintenance schedule or inspection schedule, the bridges are being inspected. So somebody climbs, the inspector climbs to the bridge, and they measure the deflection or the strain or deformation on the bridge. By knowing this deformation, you know if this specimen is permanently deformed. How can I know? I can go back to stress and strain diagram. If I know the strain, if I know the deformation, and if I know the length of the beam that I'm looking at. Let's say I went to this bridge. Okay, let's go back. Let's go through this bridge, beam, steel bridge. Okay, I'm looking at the girder, the steel girder in this bridge. This is before the service conditions, during the construction. So I know the length of this girder before the service line during the construction. And I can come back and check the deformation by knowing the gate length again during the service condition and by knowing the deformation. So when you apply load on a girder, what's going to happen? It will deflect, right? It can deflect up to certain points. If it's beyond that, it needs to be repaired. So by knowing the deformation, by inspecting and measuring how much it's deformed, you can calculate the strain and you can go back to your stress strain data. If you're talking about 836 steel, and again, I'm going to continue from this.
I have a
836.
question.
Let me finish my word and keep your question. Give me 1 second.
Okay, thank you.
Okay, put the 836. I think it's with numbers. Okay. I don't know if it's clear on your screen, but I don't want to click into it. But in this one, you can see the elastic, plastic, strain hardening, and ultimate strain, and then making down phase for 836 steel. 836 steel, 36 stands for 36,000 psi steel. 836 has breaking yield strength. Its yield strength, tensile strength is 36,000 psi. That's why it's called 836. There are 850 different type of steel. So if I know the deformation that I observe on the construction site or on a bridge during inspection, I can come back to this graph. And if that material is 836 steel, if the member is made of 836 steel, I can measure the load, how much load is applied during the service condition. And I know and I can tell that if it's beyond the elastic region or plastic region. So if the deformation is excessive, let's say 0.1 or 0.15, then I know that this material has already deformed permanently. And there are ways to retrofit it. There are ways to apply rehabilitation and fix it. But if your deformation is less than 0.02, you will automatically know that intuitively it is in the elastic region and it's good to go, and there is no problem with the member. So by knowing either the stress, applied stress, or the corresponding deformation, you know you are in what region you are in, what region you are looking into. As long as you are in the elastic region, material is perfect, it's not deformed, and it's in the safe region. But if you are beyond that region, if you are going above 36,000 psi, which is 36 ksi, let's say if you go to 50 ksi, 50,000 psi, then you already deform your material permanently. Okay, now I can take your question.
Yes, sir. So would the corrosion of a bridge, for instance, affect the deformation when you're taking measurements?
It does. Because with the corrosion, what happens is you reduce the area, cross-sectional area is being decreased. And also chemical composition of the steel is being changed. Am I right? So if you change a certain characteristic of the material, as a result, the tensile strength or compression strength of this material will change. So if you deform the material, if it's corroded, then it's not going to perform in the way that it was designed. That's why during inspection they check for corrosion, and if it needs to be repaired, they sandblast it, and then they repaint it, and they put it back in the service. As a matter of fact, I work in the Magnolia Bridge construction. It's on Mid City, Magnolia Historical Bridge, right here, and we paint it into the blue. Exactly. If you guys remember this bridge, it was not blue before. It was like this. And I worked in the construction and rehabilitation of this bridge, and I left it at the end of the construction after finishing the project. I was there for over a year. It was a long project. It was a small but long project. So this bridge was, for example, was corroded. We had to cover that bridge, tarp it, because we don't want to hurt the environment, and we had to sandblast it and then paint it. Obviously, before the paint and sandblasting, we had different members to strengthen this bridge. It's called retrofit. So we changed some of the girders, we changed some of the beams, some of the truss, or lattice truss on the right side, and then we painted. And if you guys are interested, I have the inspection reports, and I can share with you guys in the next class. Did I answer your question?
Yes, sir. Thank you.
No problem. Any other
Just out
question?
of curiosity.
Yes, sir.
So once you went to do the inspection, was that like a program that you attended, or was that an internship, or what was that?
It was my job. I worked as a field engineer with the DPW for over 2 years.
Oh, okay.
I
And
inspected.
another question. Right now, you just showed us like how the bridges are built with the steel only, like how they looked like without having the concrete on them. How
Yeah.
do they bend the steel like that?
How do they what?
Bend the steel.
Well, steel shapes, they come in pre-cut shapes already. So once you finish your once you finish your design, you submit your final design to contractor, and they order the steel specimen, steel members in the desired shape. And
Okay.
inside on site, you don't have to bend these steel members, and as a matter of fact, you cannot bend the W shape, or let's say W shape. This is W shape beam. These are big. You cannot buckle it or cut it in shape on field. I mean, you can, but it's a lengthy process. If you look at the depth, it is not feasible. But what they do, they can cut the rebars. If it's a concrete project, it's different. Then you have to work with the rebars that's going to be placed into the formwork, and then you're going to pull your concrete. Concrete rebars are small and it can cut the shapes on field, as opposed to big shape members.
Okay. Thank you.
It's two different things. Yes. Any other question? No. Okay, let's proceed. I think we're getting close. I mean, this is my first time as we go through. I'm looking at this simulation. I look at the first section, but I didn't complete it. So let's read this section, and we're about to wrap it up. The unload and reload behavior seen here is a very useful characteristic, particularly for metals. One technique for increasing the strength of the material is the process of stretching and relaxing. It's called work hardening. Okay. So the load deformation plot provides the information about only one specific size of specimen. So if we have 2-inch specimen, it is specifically for that 2-inch specimen, this load and deformation. The results of the tension test are more useful if they are generalized into a stress and strain diagram. This is what you need to do. You can generate load and deformation plot based on the given gauge length. It is not required, but it's going to be useful for you to generate the stress and strain diagram because it will be generalized format, general format. To construct a stress strain diagram from a tension test results, first thing first, you had to divide the specimen elongation data by the extensorimeter gauge length to obtain the normal strain. So this is one of the terminology that we use at the beginning. So where we use this, if I'm trying to go back to spreadsheet. Right here. So we got the load and elongation data, and I can use this data to get the load and deformation graph, but I'm trying to get the strain, normal strain. In order to normalize the elongation, I need to use the gauge length. And if I use this equation, elongation divided by gauge length, I can get the strain, normal strain. Okay, so we know how to calculate it at this point. And second thing, divide the load data by the initial specimen cross-sectional area to obtain normal stress. I already explained this section, so we don't have to go back to the spreadsheet. And then the third one is the plot. You need to plot the strain on the horizontal axis and the vertical axis. I already showed you guys how to plot it. You should have the stress on the vertical axis, which is the y-axis, and the horizontal axis, x-axis. You need to have the strain data. So when you come to your, right here, when you go back to the spreadsheet, this is your horizontal axis. You have your strain, you label it, and then you have your stress on the vertical axis. So let's continue. The load deformation plot and the corresponding stress strain diagram are shown below. Material properties that are essential for engineering design are obtained from the stress strain diagram. Let's read it one more time because this is important. Material properties that are essential for engineering design are obtained from the stress strain diagram, not load deformation diagram. Interpretation of the stress and strain curve is discussed in the companion movie. So we're not going to go into the movie. This information is more than enough for you to understand the theory section and the experiment section. So when we run our own experiment, you will have better understanding after having this knowledge and the base information about the tensile test. So we learn why we are running this experiment, what is the objective, and how we run it, and what we learn from this experiment with the results from the experiment. Any question with the simulation? No. Okay. So if there is no question with the simulation, I will ask you guys if there is any question regarding this spreadsheet. If not, I'm going to jump to other one. Is there any question with the spreadsheet? Okay. So whenever we run the experiment, I will provide this section to you. This section will be provided, and you are required to calculate this section.
Professor, are we gonna get a example of the, why am I blanking on the words? Of a lab report? Could we get like a sample copy of that so that we know how to structure it how you'd like and that sort of thing?
Yes. Yes, you will get it. This one? This one is submitted.
Don't you already have it at the bottom of the syllabus?
Do I have it? Sample report?
Didn't you put the requirements at the bottom of the syllabus?
The sample report? Yes. I had the sample report hard copy. I don't have it in my laptop. But instead of giving the sample report, I will provide you this tension report. Doesn't matter. This is sample as well. And it's more beneficial for you because you're going to be looking at the tensile test. Does that make sense? Because sample report was not on the tension test. Hello?
Yes, that sounds good.
Sounds good? Okay. So
Can we use some of those diagrams on our own report?
well, what I will recommend for you while you are doing your research, you can find this tension test setup on Google. If you ask Google about tension test, you can find different pictures, different images on Google. It's pointless to copy and paste from the sample reports given to you. You know what I mean? Or I have this book, PDF right here, that you should have it with you. So if you go to your Moodle, you should have this book. Let me see 1 second. 58. This is the book. Mechanics of
Yes,
Materials.
you did post that in the entire
Okay,
PDF.
so exactly. So you're gonna go to 58, page 58, or you can always search tensile test or compression test or torsion test. It will take you to the page that you want to see. So when you come to stress strain diagram, this is the picture that I use on the PowerPoint. You can read this section along with the PowerPoint, along with this video that we are recording and the simulation, and I believe you can construct a report. And in the theory section, you can include these pictures too. As long as you have the reference, as long as you have citations, you can use it. There are a lot of resources that is available on the internet. So feel free to choose one of them, but I want you to cite it. I want you to reference it, because otherwise it's stealing information. Okay. So from page 58 to, let's say, to Hooke's law. I'm gonna get into Hooke's law in next lecture because we're gonna cover minimum 2 hours in the next lecture by working on the data that we're gonna collect next week. And we have time. We have limited amount of time for the semester, so I'm taking it slow and I'm having minimum 2-hour lectures. So we're not gonna have any problem with the scheduling. So you can read this section, stress and strain section. And you can use the images and you can use the information given here. Any question?
Yes, sir. When will you post this this video, this recording?
When I will post this, since it's my first recording, as soon as this video is over, I will stop recording and it's gonna record it to my device, and from my device it will be on YouTube and you will have the link privately. I believe
Okay.
you tonight.
Okay, thank you.
No problem, no problem.
So this might be a dumb question, but
There's no dumb question. Go ahead.
the report is due on Wednesday, next Wednesday?
No. I made it clear in the beginning, though I think you missed that part. Report is not due next week. Due to this hurricane hurricane event, school is shut down. They are not continuing the regular hours. So I didn't go to campus. I didn't go into my lab and run the experiment. So I'm covering this theory section and I'm teaching you guys how to run this experiment before we actually run it, before I actually perform the experiment. So as of now, you know how to run this experiment. We went step by step on simulation. We learned what we are doing and why we are doing and what are the results that we are expecting to get at the end of this experiment. So when we run it, you will have your data. So right now, as of now, you don't have the data, but you have the spreadsheet template and you have the sample report. On top of that, you have the sample calculation sheet. So you have three things. You have the sample calculations. You can check your work, and you know that your graph is going to look like similar to this. If we run a perfect like flawless operation during the experiment that is successful, you should end up with this type of graph, and you should see this linear portion like we observed during the simulation. This is from the experiment that was conducted in 2017, and the simulation is just theoretical numbers. Like when you compare the simulation to this stress and strain diagram, even though they are two different material, aluminum also has the elastic region, this linear portion. So you have this, you can check your calculations once you get the data, raw data, and you can calculate the stress and strain and develop the graph. So you have this is one of the sources. You have this PDF book in PDF format. We don't have this. This is, I was about to make a PDF, but I decided to have the simulation on the internet, which was more helpful. But if you want to have this, I can also upload this one to Moodle. One of them is already in. I can upload this one as well. This is not on the Moodle, but I will upload it after the class. So if you read this, you will have an idea of how you need to construct your report. Like this is basically the theory. If you read it from the beginning, it starts with when designing structures that support any load, the engineer must investigate the mechanical properties for the materials in question. So you have a background, you explain what is behind this experiment before you start the theory. Or you can cover this section, even the experiment section or background section, under the theory. But you should have the theory section where you explain the setup, where you explain the background on this experiment, the equations. You need to explain the equations such as this, stress equation, force divided by A, force divided by the cross-sectional area. And we know F is applied force. You can find this equation everywhere. You can look at the mechanics of materials book. You can look online. The notation might be different. It might be sigma. It might be something else. It might be the load might be applied force might be P or F. But you should know that if you're trying to calculate the stress, you should divide the applied force by the cross-section area. This way you get the intensity. And then the elongation equation, the strain equation, I already explained on the spreadsheet right here in the notes section. And the modulus of
Hey,
elasticity.
let's play a different map.
What is different? Hello? Okay.
Bind.
I can hear you. Say one more time.
Fuck no.
No. Okay. Anyway, let's continue. I know it's getting late. So once you get these two equations, I also have the equation.
You got pick captain. The two best niggas. First cap.
Hello, can you please mute? Please. Thank you. Philip, Fran, mute. Okay. So you should also calculate the modulus of elasticity. And you can calculate it. It can be found by the ratio of stress experienced at that time by a strain is experienced. So You can look at this graph. It is easy to read. You can see the elastic region. You can see the yielding region, strain hardening, and necking portions. We're gonna get into this part again. You guys should know this portion from mechanics of materials, but I'm assuming that you guys haven't gotten that far yet. But if you're a senior or junior, you should know this stress and strain diagram. And one thing to mention, you can only calculate this modulus of elasticity in the elastic region. This is the reason, if you go back to sample calculation right here, the modulus of elasticity, Young's modulus, it is only calculated on the elastic region right here, 49.38. It is still up to 49.1. It is considered elastic region. How I know it? I go back down, I go down, and I see the yielding point right here. And this is the region that I can calculate the modulus of elasticity. So I need to look at the strain, I need to look at the stress, and look at the ratio between stress and strain. And it's gonna give me the modulus of elasticity. And let's explain the modulus of elasticity. And ultimate tensile strength, maximum force applied divided by the initial cross-sectional area is basically how much force, what is the maximum force. It can be applied to the material before failures. If you divide that number by the initial cross-sectional area, you will get the ultimate yield, ultimate strength or yield strength. And there is one more equation that you can use to calculate the percent elongation. You get the final length minus initial length divided by the initial length. And you can find that equation on the spreadsheet as well. Final length divided by the gauge length, and final length minus gauge length, and you divided that number by the gauge length and multiply by 100. You get the percent elongation as well as the ductility. And then you compare that ductility from steel specimen to aluminum specimen. And then you write or you summarize your results, what you have learned from your results in the below after you show your results on the tables. This table is a little different than mine. He wanted to come up with his own table, but you can use my spreadsheet. So in this, for example, in this report, the yield strength was 51 KSI as opposed to 49.1 on my calculation. We will see what will be the yield strength next week when we run our experiments. So it should be around 51, 49, or 48. It depends on the type of specimen, steel specimen that we're gonna run, test it. We're gonna be testing. So in total, you have 4 graphs. 1, 2, 3, and 4. 2 for aluminum, right here, and 2 for steel. And discussion and conclusion, it's just 2 paragraphs. Minimum is 1 paragraph. So if you can make it 2, that will be perfect. Okay, so let me upload this one on the Moodle. After the class. Any question with the report?
So do you want a, do we use Excel and Microsoft Word for the lab report?
Yes, if you can. What else you'll be using?
I don't know.
You tell me. If you can use another software that's going to give me the proper lab report, it can be converted to PDF. So Also, I want to mention that in weekend in advance because you don't have a report next week. But when you write the report, this is the main problem that I faced last semester during the online teaching. So you come here to Word. There's the Word file. Give me 1 second. Anyway, let me pull up this one, but I will show you this. So you go to Files, you go to Print. So please do not submit a Word file and spreadsheet file separately. When you finish your report, when you insert your tables and graphs into the Word file, you're gonna come to Print, and you're gonna print to PDF. So you print it, and you can write, this is syllabus. This way, I have only one file that I can use, and it's a PDF format. It's in the PDF format. But if you have the Word file, I cannot create it on Moodle. It is a painful process. So I have to download your submission, convert it into the PDF, or if you submit in 2 files at the same time, spreadsheet and the Word file, I have to combine them, and I have to convert the PDF, then grade it. So to make it easy, I will mention again and again. I'm sure there will be a couple of students that are going to be doing the same thing, submitting 2 different files, 3 different files, but I don't want it. I want only one single PDF, and it's easy. It's not too hard. You just go and print. Instead of printing on paper, you're going to print on the PDF, and it will be ready for me to grade. Any question? Okay. If there is no question on this part, I can finish this lecture, and next week when we come back, we can start working on our data. Next week we will have this column, these 2 columns, and I will work out these calculations. So I will write the equations. I will calculate the stress and strain, and we're going to look at the stress and strain diagram together. We're going to analyze it if we can, if we have time. Usually only 3 hours is allocated for this lab, but since we have difficulties, I'm going to have 2 class hours, 6 hours dedicated to tensile test. But we have time, I have time, and we have enough weeks to cover 7 labs. So if there is no question, I can finish this class and you guys can go to dinner. But if you have questions, you can stay after class and I can answer questions one by one. Otherwise, class is over.
Is there anything that we need to have done, or is there anything that you want us to do before next week, or just wait until next week?
So before next week, on that book, PDF in PDF format, Mechanics of Materials book, from page 58, let me go back to this book. If I can pull up this book again, right here. It is starting from page 58, actually 57, section 2.3, stress and strain diagram. Please read that section. It's the homework, but I will not accept any reports, or I'm not expecting you guys to submit anything. But it's good for you to read. This is your assignment. It's up to you if you want to read it. But if you read it, you will have better understanding of this tensile test experiment. I recommend it. It's I think 4-page or 5-page.
Do you also want us to run through that simulation a few times?
Oh, definitely. Definitely. If you run the simulation, that will be perfect. But there is no.
You'll post that link after class?
Yes. Yes, that's what I will do. 2 things that I have to do is the link, simulation link, and then the sample report. But please do not copy and paste the same report from my sample report. Please. It doesn't matter if it's an image or picture or table or graph or wording. Everything is for you to, all those files for you to reference it, but not to copy it. You can summarize it. You're free to summarize whatever you have on the Moodle or online, as long as you cite it.
Is the objective supposed to be in our own words also?
Or you can, no, you can get this objective section. But you can always paraphrase it, you know? You can use your own words. You can change the word, tweak it. Keep the same meaning, same objective, same goal.
Okay, thank you.
So as long as I know, let's put it this way. You are giving away your report outside on the street to people who don't know anything about engineering. If you go on the street, if you ask somebody what is strain, what is stress, what is ultimate tensile strength, they don't know anything. If you ask them what is tensile strength, they don't know anything about tensile strength. But if you give them your report, and if they read it, the objective of this report, now they know what is the objective. And when they go to this section, theory section on the report, on the sample that I showed, in theory section, you explain what is the strain, and you explain why we run this test. So even a person on the street who doesn't know anything about engineering, they should be able to understand what you are talking about. So write your report in simple terms. So I know that you're not copying from a book, because when you look at the book, it is all theoretical words. It's complicated, but you can simplify, like I simplified the terminology. Once you simplify it, it will be easy for you to understand, memorize, actually understand the logic behind it, rather than memorizing. Because if you memorize the definitions, you will forget the definition in next week or in maybe next semester. But if you understand the logic behind it, what is the purpose of this experiment? What do I get after this experiment? Or what answer I'm looking for, then you will be in better shape.
I have a
All
question.
right, Barrios? Piero?
Yes, sir. I didn't ask that question, but I heard you.
I know. Good. I was just checking if you listened to me.
Oh, yeah.
Good.
I was listening in the car driving over here.
I know. Thank you for keeping up.
I have a question.
Go ahead.
Yeah, let's say I write a report and I email it to you and say and ask you for pointers on how to make it better or how to where to improve.
Actually, what we can do, I prefer Zoom meeting.
Okay.
If you shoot me an email and if you want to set up a meeting on Zoom and you can share my screen, I can share your screen. It's better for me to read it and ask you a question rather than send an email back and forth.
Perfect.
You know, let's make things easier for you because your time is important, valuable, my time is valuable. Let's respect each other and finish it on time, just in time. Whenever you have questions, just shoot me. And if I don't respond your email on time, and if you are running late on your report, you can just tell me, hey, you didn't respond. And I already know. I'll go back when I'm grading papers. If your report is late, and if you already send me an email asking for help, and if I didn't help you on time, that's on me. I take responsibility, and I don't ask you for a report until I give you your answer. Then you can proceed and write your report and finalize it and submit it.
Okay, thank you.
So considering this COVID-19 and the hurricane and everything, I will be going easy on grading. But it doesn't mean that I will accept late reports after 2 weeks, 3 weeks, or 4 weeks. That's not the case. So you're gonna submit it on time, whenever it's scheduled, due date. And you will send me an email if you come across any problems, if you have any questions. And you have my number. If you go back to first slide, this is my number at the bottom. It's for emergency only. In the case of, for example, if we don't get response in 2 days, something is wrong, that I didn't see your report or went with my junk mail or anything can happen, you can just give me a call. It's better to solve this problem over the phone rather than sitting down and writing an email, one-page email, one by one.
Okay.
Right?
Yes.
Okay, perfect, perfect. So I believe the class was successful. So we can finish this class and we can meet next time on Wednesday at 3:30. Okay? Thank you guys for coming to class and see you guys next week.
Thank you.
Thank you.
See you next week.
Yeah, bye-bye.
Is it cool if I just ask a question because I just came in late about the beginning?
Go ahead.
With the test, we're not putting anything in the notes box, right? Like we don't actually
no,
like.
those are my notes. The note section, those are my notes for you to look at it and understand how
Are those like the formulas that we can use like in Microsoft Office? Like, are those the formulas we can use to get all the numbers instead of having to manually go through and like put them all in?
Right, right. So these notes are for you to take a look at it and reference it when you are calculating the stress and strain. So when you look at the notes, you see that stress can be calculated by using the applied load and the cross-sectional area. When you divide the applied load by the cross-sectional area, you will get the stress. And you're going to come to strain. If you go one by one, the first step, you're trying to calculate the stress for this section, for this line. And you calculate the stress. Now next step is the strain. So you come here, you see how you can calculate this strain. And if you want to know what is the definition of stress and strain, you go back to the book that is on Moodle. You can look at the definition. Or you can Google it, what is strain, what is stress. I already mentioned what is stress and what is strain, etc. But this is the equation that gives you the stress and strain by knowing the load and the elongation and the cross-sectional area.
Oh, I meant like the equations like in like Office that say like B4 divided by like E9 or whatever, but that's okay. That's okay.
Oh, okay. So you on Office Word or spreadsheet?
Spreadsheet, like what we're in right now.
Yeah, you can put it in, like I put it in at the beginning. For example, B7 is for the applied load right here, 1 kip. So this applied load B7 at the cell B7 is divided by cell B3, and this cell B3 corresponds to cross-sectional area. So once you enter these values, these cells into the formula, it will calculate for you automatically.
Down, right?
And you can drag it down, and it will give you the number as you go, like 5, 6, 7. All you need to do is fill the first part, and then let's say for the purpose of this example, my bad. Let's say I got the strain, I just drag it down, it calculates for me. And then once you finish it, you will just come here, the data section, you're gonna copy this and paste it into the Word file.
In paste in Word, right?
And you can even have the notes section, but I don't want you to submit the Excel spreadsheet including with the Word file. There is no Word file, there is no Excel file that is going to be submitted. You will print into PDF, so you will convert your Word file to PDF, and I will receive only PDF file. That makes sense? Yes.
Yes, sir.
Okay. What else? Okay.
What does a $sign mean on the Excel sheet?
$sign, it locks the cell that you are working on. This
Okay.
$sign. Okay, if I don't lock the cell, what's going to happen is, okay, so I'm starting from the beginning. This is my cell. I look at my equation, P over A. I go to P, select it, and I divide that P number by the area, cross-sectional area. Right, that's what I did. It's correct. There's nothing wrong with this. But when I want to calculate the remaining portion, look what's going to happen. It's not calculating. Why? I click here and I see that as the load value changes, that cell is also going down. So it knows where you pick up the cell, and it's when you scroll down, it also changes. Sorry, the cell also changes cross-sectional area cell. It goes down. So in order to prevent this, you lock the cell with the $sign. When you put the $sign, your cell stays the same. It doesn't change. You should do it at this.
Oh, okay.
That makes sense?
Yes, sir. Thank you so much.
I did the same thing for gauge length. And for you guys to complete the aluminum section, there's blank, this page is blank. What you can do is, let's delete this one. So I'm gonna come here. I'll click on move or copy. And I can create a copy right here. And this is the copy. And I will write it as an aluminum. It's gonna save minimum 2 hours from your work. So I already have my steel that I was working at the beginning. Now I have the aluminum. So if I know these numbers for aluminum, right, you can delete this one because this was copied from the previous page. I can enter the diameter, gauge length, and final diameter. Let's say diameter is 0.6, gauge length is 2 again, and the final diameter is 2.5, 1.4, sorry, and the final length is 2.6, and final cross-sectional area. You can just put the equation from here, pi d squared over 4, and you can enter the numbers 1,000, 2,000, and let's say 5,000, 6,000, and the corresponding elongation value that this will be given. And you can calculate the stress and strain for aluminum. And this is data for aluminum. Since you copy the same spreadsheet for aluminum, you also have the graphs, count with the bonus. So this way, you're not wasting your time to make the same table and make the same graphs over and over. It's just one step. You move or copy, click, and then you can create copy. It's easy. It saves time. Any
Okay,
questions?
thank you.
No problem. What else? No question? Austin?
Nope, that's it.
I'm assuming that you guys are staying because you guys have question. If there's no question, I can stop the meeting.
Yep, that's cool. See you later.
Okay, see you guys later. Have a good night.
Okay, thank you.
Bye.
Thank you.
Thank you.
Thank you. Bye-bye.